Hello everybody. In this video we're going to work through 3 related rates examples. So a few reminders about working with related rates, and there are quite a few items on this list, and hopefully you'll be able to see how they play out in the 3 examples. But here are my thoughts on it. You want to identify relevant quantities and give them variable names as necessary. Identify which rate you are looking for and be aware of the moment at which you are supposed to find that rate. Look for the most elegant relationship between relevant quantities. When you take derivatives, you'd rather deal with as simple a relationship as possible so your derivatives don't spiral out of control. Be willing to use more than one relationship if it simplifies calculations. Now, in these 3 worked examples, we won't see a good example of this, but this is something to keep in mind. Do not substitute transient information before differentiating. So if a quantity Q is changing and you want to find a certain rate when Q equals 10, you don't want to substitute 10 for Q before you differentiate, because that'll mean you've basically made Q a constant function. So make sure that you differentiate first before substituting in information that happens to be true at the moment you care about. However, feel free to substitute quantities that are actually constant. So for example, if one of your quantities was constant throughout, then you can substitute in your relationship that constant instead of using a variable name. Take the derivative with respect to time, apply all the usual rules of differentiation, and be ready to apply implicit differentiation. So we'll see several times in these worked examples where you have to remember the chain rule, and there will be a product where you take the derivative of your variable with respect to t, and that often happens implicitly. Use the given information to analyze the moment in question. So you should gather all the facts that have been presented to you, and unless the question has been posed incorrectly, there's enough information to put into your equation, and you should be able to solve for the rate in question. And then finally, you want to keep track of your units. So in 2 ways. One is to make sure your units are consistent. So if you're using centimeters over here and meters over there, you want to make sure that you can convert properly, for example. And the other thing is you want to present your answer with the correct units. So here's our first problem. Water leaks from a conical tank at a constant rate of 0.4 cubic meters per hour. So here you can see schematically we've got the water leaking out of the tank at a rate of 0.4 cubic meters per hour. The tank is 4 meters deep and the radius of the tank is 2 meters. So we'll label those dimensions in our diagram. How fast is the water level dropping when the level of water is 1 meter? So the water level, let's give it a name. Let's call it H. And now our question, how fast is the water level dropping, amounts to asking what is the value of dH dt, the rate of change at h with respect to time t. And the moment we want to figure out this quantity is when h equals 1. So our question boils down to what is dH dt when h equals 1. Let's give the radius a name, r, because we're going to have to find the volume of this amount of water. This is going to be the amount of water we have in the tank. And from geometry we know that this is going to be 1/3 pi r squared h. Now it's time to use a little right triangle trigonometry. These 2 triangles are similar. So the ratio of r to h is the same as the ratio of 2 to 4. So r over h equals 2/4, which means that r is 1/2 h. Now we can substitute this directly into our formula for the volume of the water, simplify that, and we get that the volume is equal to pi over 12 h cubed. So now we can take the derivative with respect to t. dv dt, the rate of change of volume with respect to time, is equal to power rule 3h squared. And then notice dH dt. Here's one of those instances where the chain rule pops in. We have to take the derivative of h, which is implicitly a function of t. We have to take the derivative of h with respect to t, multiply it here. And so that's a possible place where you might, if you're not careful, forget to apply the chain rule. We'll move this formula down into the lower left. Now we're going to remind ourselves that dv dt is constant. We know that that is negative 0.4. So we'll substitute that into this equation. And when h equals 1, obviously we can swap out h squared for 1, we just get negative 0.4 is equal to pi over 4 dh dt, which is solved for dh dt. Negative 0.4 is negative 2/5, so we can actually get an exact expression here. dh dt is negative 8 over 5 pi meters per hour, and numerically that's about negative 0.509 meters per hour. Notice that the fact that dh dt is negative is good. We want that rate of change to be negative because the water's leaking out of the tank. The height should be decreasing, so dh dt really should be negative. If we want to, we can switch units to get a different feel for how fast this is happening. This would be about negative 0.014 centimeters per second. So let's tidy this up. At the moment the water level is 1 meter high, the rate at which the water level decreases is approximately 0.509 meters per hour. All right, next problem. At noon, a car starts traveling north at a constant speed of 50 miles per hour. At 2 p.m., a car leaves from the same place, traveling east at a constant speed of 60 miles per hour. At 5 p.m., at what rate is the distance between the two cars changing? So let's give this distance a name. We'll call it capital D. And we'll also give names to the distances that these cars have traveled. We'll call them x and y respectively. And the Pythagorean theorem does a nice, elegant job of connecting all these variables together. D squared is equal to x squared plus y squared. And the question at hand really amounts to this. What is the rate of change of d with respect to t at 5 p.m.? What is the derivative of d with respect to t at 5 p.m.? So we will go in here and take the derivative implicitly, and notice that the chain rule really shows up 3 times here because d, x, and y are all implicitly functions of t, and that chain rule needs to occur in each of these instances. And now we'll just cancel the 2's. All right, what do we know? We know that the rate of change of x is constant at 60, and the rate of change of y is also constant, it's 50. And at 5 p.m., the northward car has been traveling for 5 hours at 50 miles per hour. So we know that y at that moment should be 5 times 50 or 250 miles. Similarly, the eastward traveling car has been going for 3 hours at 5 p.m. It started at 2 p.m. So 3 times its rate, which is 60, constant. 3 times 60 is 180. So x is 180 at that same moment. So the distance between the cars, we also need to know this. A simple application of the Pythagorean theorem will do. And if you prefer to sort of work out with pen and paper, you could factor out the 10 and find that it is 10 root 949. In any case, we are now in a position to write down the rate of change at 5 p.m. So we'll move over here and we will plug in all the information. We have all 5 bits of data that we need at 5 p.m. And so we plug that in and we can crank this out and we get about 75.6, and the units are miles per hour. So at 5 p.m., the distance between the two cars is increasing at a rate of approximately 75.6 miles per hour. Final problem. A lighthouse is 200 meters from shore. So we'll have a little diagram here. There's some water, there's the shore. We're looking straight overhead, so that's our lighthouse, and it's 200 meters from shore. The lantern rotates counterclockwise viewed from above at the rate of 6 revolutions per minute. So we're just going to put 6 revolutions per minute on the side there. A revolution is not a measure of angle, so I'm not willing to call that d theta dt quite yet, but we'll come back to that. How fast is the beam of light traveling along the shore at the moment the beam strikes 300 meters beyond the point on the shore closest to the lighthouse? That is a mouthful. Might be easier just to picture what's going on here. Here's the point where the beam strikes the shore. We will call this distance from the shortest point, we'll call that y. And now we recognize that this question is much more easily posed as follows. What is dy dt when y equals 300? Please take a few moments to make sure you understand how this wordy version of the question really does translate into this far more succinct version when we're allowed to use the language of calculus. What is the rate of change of y with respect to t when y equals 300? Let's call this angle theta. And now we're ready to tackle the question of d theta dt. So we'll notice that there are 2 pi radians per revolution, and there's 1 minute in every 60 seconds. So if we take this product and do the unit analysis, we see that we get a quantity which is measured in radians per second, which is the natural way to measure d theta dt. D theta dt is pi over 5 radians per second. We can read off from our diagram a very elegant relationship between y and theta. Tangent of theta is equal to y over 200. And therefore, when we take the derivative, secant squared theta d theta dt equals 1 over 200 dy dt. Please don't forget, here's a possibly subtle application of the chain rule. Theta's a function of t implicitly, so we need to multiply by d theta dt to apply the chain rule here. And we solve for dy dt, 200 secant squared d theta dt. Now when y equals 300, we need this moment when y equals 300. We need to figure out what the value of secant is, secant theta. So we can draw a picture. Here's substituting in 300 for y. Now, we could work with this triangle directly, but we could also scale it down to a similar triangle by dividing through the sides by 10. In which case, this hypotenuse, easily calculated to be root 13, and we could, of course, scale up to work with the actual triangle in the picture. But if we need secant theta, we can already read secant theta from this diagram. Cosine is 2 over root 13, so secant is root 13 over 2. And now we have all the pieces in place. So we're going to rewrite dy dt over here. Dy dt is going to be 200 secant squared theta, which is 13 over 4, times d theta dt, which is pi over 5. That simplifies to 130 pi, or about 408.4 meters per second. So here's what we might put for our punchline. At the moment the beam strikes the shore 300 meters beyond the point on shore closest to the lighthouse, the beam is sweeping along the shore at a rate of approximately 408.4 meters per second.